Okay, so we'll wrap up elastic collisions here. Let's look at what goes on when we have a spring, and it is part of the system for a collision. So we have two blocks, mass 1 and mass 2, and a spring attached to mass 2. We've got some velocities given, and let's see what we can do to do some analysis on it. A block of mass 1 has a 1.6 kilogram mass, initially moving to the right with a speed of 4 meters per second. Okay, although they call it speed, it's velocity in the x direction. And it's on a frictionless horizontal track, so we can disregard friction. It collides with a massless spring. So again, whenever you see something like that, massless spring, we're not even going to worry about any of the mass of the spring. All we'll be interested in is the K, the constant, which gives it its tensile strength and its springiness. And it's attached to a second block, mass 2, which is 2.1 kilograms, and it's moving in the opposite direction to the left. So it's moving in the negative direction, mass 1 is moving in the positive direction, and mass 2 is moving at a speed of minus 2.5 meters per second. The spring has a spring constant of 600 Newton meters. Okay, so you can see the way it's laid out here. What's going to happen? The two are going to collide with each other, mass 1 and mass 2. The spring is going to do its thing, and what we're going to do is we're going to measure the displacement of the spring going into compression as the distance for this problem. So at the instant that mass 1 is moving to the right with the speed of 3 meters per second, we want to determine the speed of mass 2. We need to find the velocity 2 final when block 1 has a velocity of 3 meters per second. So there's our diagram. We're going to look at this in terms of total momentum being conserved. So we start with our conservation of momentum relationship. So you should be used to seeing that by now. Mass 1, velocity 1 initial, plus mass 2, velocity 2 initial, and the same thing on the other side for the final values. So since we're solving for velocity 2 final, that's this term over here, what we're going to do is we're going to move everything that except m2, v2 to the other side of the relationship, and then we're going to factor m2 out, and that's what we have here. So we've got mass 1 velocity 1 initial plus mass 2 velocity 2 initial, just as you see it on the left side, and then we subtract mass 1 velocity 1 final from the right side, moving it to the left side, and then dividing through by mass 2. So in this case, we've got values for every one of those terms. So we can plug those values into that relationship, do the products, do the sums and differences, divide by 2.1 kilograms, and once we combine everything, you can see that we end up with 2.1 kilograms into 640, and that gives us minus 1.74 meters per second. Okay, so on the next question, they ask, find the compression of the spring. Determine the distance the spring is compressed at that instant. So now we go back to our energy relationship, energy, the conservation of energy for the system. So since everything in this case is kinetic except for the potential in the spring, so we can use kinetic energy 1 and 2, initial, potential energy of the spring, and we set it equal to the final values. So now, again, we've got all of our terms. We've got kinetic energy, potential energy of the spring, and the same thing on the other side. So as we move our terms around, again, noticing that the potential energy of the spring is initially 0 because it is not in compression, and then we still have all of the other terms. Okay, so now we're going to solve for the distance that the spring is compressed. So that is our x sub f squared. So we're going to isolate that to the left side of the relationship. We're going to move everything else to the right side. Again, since the 1/2 is common in every term, we can take that out. And what we're left with then is the distance in the spring final squared is equal to, now we're going to factor out mass 1 and mass 2 from our relationship and divide by the spring constant. So once we do that, take the square root of both sides, now we have the equation ready to start dropping numbers in. So when we do so, we drop all of our values in, all of our given values, we divide by 600 newtons per meter, and we get a compression or a distance that the spring has compressed of 0.173. Moving on to glancing collisions then. Glancing collisions is a more common type of collision. The glancing collision occurs when the colliding masses rebound at some angle relative to the line of motion of the incident mass. So when velocity 1 of the first mass strikes the velocity or the mass 2, it ejects at some angle. So let's take a look at an example. A car with a mass of 1.5 times 10 to the 3rd kilograms traveling east at a speed of 25 meters per second collides at an intersection with a 2.5 times 10 to the 3rd kilogram van traveling north at a speed of 20 meters per second. So we've got all of our masses, we've got all of our velocities. Find the magnitude and direction of the velocity of the wreckage after the collision, assuming that the vehicles undergo a perfectly inelastic collision, that is, they stick together, and assuming that friction between the vehicles and the road can be neglected. So they're taking a lot of things out we don't need. So use of conservation of momentum in 2 dimensions. Again, kinetic energy is not conserved. So we start with our summation. We're going to sum all of the momentum x terms initially. So we get the mass of the car, the velocity of the car. We get 3.75 times 10 to the 4th kilogram meters per second. Then we're going to sum all of the momentum final in the x direction. So in this case, we've got the mass of the van and the car that are joined together now, times the velocity final, but we have to take the cosine of theta so that we can determine the angle associated with the two cars when they come to rest or when they hit and glance. Okay, so we have 4 times 10 to the 3rd kilograms. That's the sum of the two vehicles. The final velocity times the cosine of theta. So in this case, since momentum is conserved, momentum in the x direction initial equal to momentum in the x direction final. So we set those two values equal to each other. So in this case, we have a value, 3.75 times 10 to the 4th kilogram meters per second, but we still have terms in the second expression, 4 times 10 to the 3rd kilograms, unknown velocity final, and angle theta. So let's determine then the y components. We've done everything we can in the x-axis. Now let's determine what's going on in the y-axis. So the mass of the van and its velocity then comes out to 5 times 10 to the 4th kilogram meters per second when we sum them, or when we take the product and get our momentum. So that's initial. The momentum in the y direction final, again, the two vehicles are stuck together. We have v final sine now of theta for our value. So we've taken that as far as we can go. So just like we did in the x direction, we're going to set the two equal to each other because we have conservation of momentum. And when we set them equal to each other, we get this expression. Now what we're going to do is we're going to create a ratio or a relationship between the two. So you notice we've got a fraction now. So we've got the x terms in the numerator. We've got the, we've got the x terms in the denominator. We've got the y terms in the numerator. So as you look at this, you can see that on the left side, we've got values there that we could deal with. On the left side, the same thing, except for we've got a sine and a cosine. So what we have to do is we have to go to some trigonometry. And there's a identity that says that the sine of theta divided by the cosine of theta is equal to the tangent of theta. So we can take that whole sine theta, cosine theta, turn it into tangent theta, and now we're solving for the tangent of theta, which will allow us to solve for theta. So it gets rid of that entire part of the expression. Notice that the velocity finals then cancel out, and the 400, or the 4 times 10 to the third kilograms cancel. So all of that goes away, and all I'm left with is my angular relationship set equal to 5 and 3.75 times 10 to the fourth kilogram meters per second. So now when I do that, it just becomes a quotient here, and I get a value, a unitless value of 1.33, because the tangent is a unitless value. So now if I take the inverse tangent of both sides, what I get now is the angle. So the angle of inverse tan 1.33 is 53.1. Now that I have that, I can stick that value back into either of the relationships. Let's put it into the value with the sine of 53.1. Multiply those together, divide it into 5 times 10 to the fourth kilogram meters per second, and I get a velocity final of 15.6 meters per second. So what we've looked at is we've defined momentum, we've defined the impulse momentum, we've defined average force, we've looked at collisions, elastic like billiard balls, and we come up with this relationship: momentum conserved, energy conserved. Inelastic like a rubber ball, momentum conserved, energy not conserved. And you'll notice that we've got this expression: perfectly inelastic, then stuck together, momentum conserved, energy not conserved. And that wraps up 6. So when we move on, we're going to look at the circular motion and the law of gravity.